Good afternoon, Internet. I am Matt Buyak, and in this video, we'll be taking a look at the 41st problem from the Project Euler Problem Archive. But first, you may have noticed that my background looks a little bit different today, and that's because I recently relocated from San Francisco, California to Columbus, Ohio. I've been very busy getting that move accomplished in the last month, so I haven't had much time to make videos. But now I've got my computer set up, I've got my internet connection hooked up, and so I'm hoping I'll be able to make many more videos for all of you in the coming weeks. That out of the way, let's take a look at our problem. So this problem asks us to find the largest pandigital number that is also a prime. Now, we've had a number of Project Euler problems that involve pandigital numbers, but I believe they've always referred to a pandigital number as specifically a 9-digit pandigital number. That is, it has the digits 1 through 9 exactly once each. For this problem, we're allowed to have pandigital numbers with fewer than 9 digits. That is, for example, it might have the digits 1 through 4 exactly once each instead. So in order to solve this problem, we're going to need a way to efficiently generate pandigital numbers. And the way that we'll do that is by using this function here, next permutation. Exactly like it sounds, it just takes some collection of objects and cycles through all the possible permutations of those objects, returning false when it gets back to the first permutation. So we'll be using that to generate pandigital numbers. We'll also need a way of testing to see if those numbers are prime. And a while back, I did a whole series of videos in which I wrote a class for generating primes, testing numbers to see if they are prime. And we will be using that in this solution, but not for doing primality testing. And the reason for that is because that primes class works very well for numbers up to 1 million, 10 million, something in that range. But once you start to get to numbers, 100 million, close to 1 billion, it really starts to struggle. And the reason for that is the way our primes class works is by generating all the primes up to the number in question, and then caching the result. And the algorithm that we use for generating primes, called the Sieve of Eratosthenes, is what's referred to as an n-squared algorithm. That is, roughly speaking, if you double the size of the number that you are testing, our class isn't going to take twice as long, it's going to take 4 times as long. And so it really starts to slow down once you get up to the larger values. We'll still use our primes class for generating primes, but for doing the prime testing, we're going to write a little bit of special purpose code that works well for large numbers. And so now with our strategy clearly laid out, let's get into writing some code. As usual, we will copy our template directory to make our problem directory. And we'll open up our main.cpp. Okay, as I mentioned, we'll be using our primes class, and so we're going to need to include primes.h. We'll also need that next permutation function, which is defined in algorithm, and so we will also include that. And we'll need to modify our makefile to link in our number theory library, because that's where our primes class lives. Okay, So the first thing we want to do is to iterate over the digits, or the number of digits in our pandigital number from 2 up to 9. So we'll say for int n equals 2, n less than 10, plus plus n. We'll need a container for the digits in our pandigital number so that we can use next permutation to permute them. That is, we can't just store our number as an integer because next permutation doesn't view that as a collection of digits. On the other hand, if we use a string to store our digits, we can do std string digits. And actually, let's initialize that to just the digit 1. A string is a collection of characters that the next permutation function can work on. So at the beginning of each iteration of this loop, we're going to add the next digit that we need for our pandigital number. So the first iteration, we will add a 2 to the end. So we'll have the digits 1 and 2. On the second iteration, we'll add the digit 3. So we have 1, 2, and 3, and so on. So let's say digits dot push back 0 plus n. So this is just the character code for 0. Adding n to that will give us the character code for the digit n. And then we're going to say while std next permutation digits dot begin digits dot end. And while we're doing this, we're going to need to keep track of the largest prime pandigital number that we have found. So let's say int solution equals -1. And we'll update this value as we find candidate solutions. We'll also need an instance of our primes class. So let's say primes p. Okay, so at this point, we've got our pandigital number represented as a string. We need to convert it to an integer. So we'll say int p is equal to a to I digits dot c stir. So this c stir is just giving us our pandigital number represented as a C-style string, which can be accepted by this function a to I, which converts from a C-style string to the corresponding integer. Then we'll just say if is large prime, and this is going to need our primes class and also the number that we're testing. So if it's a prime, then we'll say solution is equal to std max solution and p. That is, if we have found a prime pandigital number, then update solution with the larger of the two between solution and our new candidate solution. Then once we reach the end here, we just say printf solution equals solution. Now we just need to implement this function here, is large prime. So let's do that up here. All right, so we'll say bool is large prime. Primes reference p and int p. Actually, let's use n here because we're going to use p inside the function to represent an actual prime rather than a candidate prime. Okay, so the technique that we're going to use for doing primes testing is to just try each of the prime numbers up to the square root of n. And this works because if there were a prime larger than the square root of n, there must also be a prime divisor of n which is less than the square root of n. So we only have to check primes up to the square root of n. Note that even for a number like 100 million, the square root is only 10,000, and so that's a relatively small number of iterations that we need to do in order to test whether it is prime or not. So let's just say int p is going to start off at 2. We'll need an index to correspond to which prime we're currently testing. So we'll say I is equal to 0. That is, 2 is the first prime. And then we'll say while p times p is less than or equal to n. And we'll say if n mod p is equal to 0, that is, if p divides n evenly, return false. That is, n is not a prime. Okay, so then we'll say increment I and get the next prime. So we'll say p dot get prime I. So we're getting the ith prime. Oh, and we'll need to actually assign that to p. Okay, then if we have tried all the primes up to the square root of n, and none of them divide n, that means n must also be prime, so we'll say return true. Okay, let's go back to our shell, go into our problem directory, and make. Apparently we've made some mistake. Oh, I haven't actually included string. Okay, and our solver says that the solution is 7,652,413. So let's go back to the archive here and scroll down to the 41st problem. And we can see that that does indeed match our solution. So thank you once again for watching this video. In the next video, which hopefully won't be coming out too far in the distant future, we will tackle problem number 42. Hope to see you then.